a binary tree which is the heap structure. So we're going to have A, L, G, O, R, I, T, H, M. First construct a binary tree, and the order or where these elements are placed into this binary tree or into this structure is not very important. This is going to say, for simplicity, we just place each of the elements one by one, level by level. So A, L, G, O, R, I, T, H, M. All these letters, all these elements were just placed in this order. And clearly, this is not a heap yet, because having a maximum heap, we need to have all the parent nodes satisfying that the value stored in the parent node is larger than value stored in children nodes. So what we're going to do is, for each of the parent node, from the last parent node to the first parent node, we're going to process them one by one. So the last parent node is O. And for each of the parent node, we want to make sure that it is larger than both children nodes. Otherwise, we're going to perform some swaps. So O is greater than H, O is greater than M, so there's no problem here. No swaps, though we made two comparisons. Then the second last parent node is G. We want to make sure G is larger than I and T. Well, in this case, clearly the condition is not satisfied. So what we're going to do is we're going to pick the larger one between I and T and then swap with G. Because we want to make sure the parent node is the largest node among the parent node, left child, and the right child. So in this case, we're going to have T swapped with G. Then next parent node, which is L. L compared with O, L compared with R. Clearly, L is not the largest, so we need to swap with the larger one between O and R. So we will have L swapped with R. And that's it. And for the first root node, the parent node, which is a root node A, we will have A compared with both R and T, and then swap with the larger one. So we will have A swapped with T. And remember that every time after a swap, the parent node that we swapped down, we still need to have that node compared with its new children nodes. So we will have A compared with I and G, finding that I is the largest one. So we will have another swap between I and A. And now since A is already a leaf node, we don't need to compare with the children nodes, and that's it for the bottom-up approach. Quickly go through the idea again. We first place all the elements into a binary tree which satisfy the heap structure. So nodes are ordered level by level and within each level from left to right. Then we identify for each of the parent node from the last parent node or from the bottom level parent node to the first level parent node. We compare the parent node with children nodes. If the parent node is already the largest, then we don't need to do the swap. Otherwise, we'll need to perform a swap with the larger child node. And if we perform the swap and the parent node is not a leaf node, we need to compare the swapped parent node with its new children nodes again, until we make sure that the parent node is in its correct position. We repeat this process for each of the parent nodes from the bottom level to the first top level. I think we discussed this in the lecture that the time complexity for this approach is linear. We clearly don't have time to prove it in the tutorial, but I think it's mentioned in the lecture. It's also proved on the textbook, and if you're interested, feel free to go through that. Then I'll probably just spend 1 minute talking about heap sort. heap sort is based on heap maximum heap. And the idea is that in the maximum heap, we know the maximum element is at the root node. So what we can do is we can swap the maximum element, which is a root node, with the last element in the heap. And after swapping them, we're going to reduce the size of the heap by 1. So we're excluding the largest element. And since we just had an element swapped to the root node, but that element might not be the largest element. So we're trying to heapify by comparing that element with children nodes, and then we may need to perform swaps to make sure that that element is placed into a correct position. So every time we swap the largest element to the end of the heap, decrease the size of the heap by 1, and try to reheapify by swapping the root node with children nodes. So at the end, we're going to have the size of the heap equals to 0. But if we look at the nodes, if we look at the elements stored in that heap, all the elements should already be sorted. Because every time we are swapping the largest element to the last position, so we will eventually have a sorted array. We might have a question next week to further talk about this in detail, but for today, I think we just need to, the main purpose of today's workshop is we had an idea about tree traversal, and then we talked about how we can construct a heap by using 2 different strategies, and also how a heap can be used for sorting a collection of elements. So I think that's everything I need to talk about today. Thanks for joining us, and I'll see you. I think I will see you in 2 weeks. Next week is a non-teaching break, right? Thank you, everyone.
I'm just wondering the time complexity of this heap sort.